Okay, so today we'll talk about multi-qubit systems. So we've talked generally about the state of quantum systems and actually how you can have quantum systems of different dimensions. So for example, you can have a dimension 4 quantum system or a 4-level quantum system. Theoretically, if you have a spin 3-house particle, like some kind of baryon, it can have 4 different basic states. And you keep track of its state with a unit vector of 4 complex numbers. And then we saw last time that the way these states can transform is via unitary transformations. Okay, so it can change state through the application of a 4x4 unitary matrix U. Basically a rotation or reflection in 4 dimensions. And then finally, you can measure your system. And this is the rule. You have this measuring device that reads out the 4 possibilities between 1, 2, 3, and 4 with these amplitude magnitude squared each. OK, so that's possible. But by far, the most common way you'll ever have like a 4-dimensional or 4-level quantum system is not by having some particle with 4 different spin values, but by having 2 qubits. OK, so qubits are the most common object that we'll study. So the most common way to have a 4-dimensional system, 2 qubits. For example, you might have 2 photons and be considering their polarization. OK, so in this example, if you view the 2 photons jointly, then they have 4 basic states. So if we say 0 is horizontal polarization and 1 means vertical polarization, then the 4 particles can, the 2 particles can be like horizontal horizontal, horizontal vertical, vertical horizontal, or vertical vertical. Okay, and so the joint state of these 2 particles would look like this. Alpha 0 0, amplitude on 0 0, and the other 3 possibilities. Okay, and here the first coordinate refers to the polarization state of the first photon, and the second for the second photon. Okay, and similarly, if you had 3 photons, you would get an 8-dimensional state. If you have 4 photons, you get 16-dimensional state. And when eventually you get into quantum computing, you might have 100 photons, and then you have a 2 to the 100-dimensional state. OK, so let me tell you what we're going to do today. We're going to talk about how you analyze systems that don't just consist of one abstract d-dimensional vector, but are composed of multiple qubits. OK, so today, let's say Alice has some qubits. Okay, we're going to use the standard computer science characters here, Alice and Bob. OK, so Alice gets out a photon. And it's in some state psi. And let's say also that Bob has his own qubit in state phi. And let's say both of these are qubit states. So they're both unit vectors in 2 dimensions. OK, so maybe they separately prepare their photon in these 2 states, and they get them together to have a play date. They're going to put them into some kind of joint physical device that interacts with them simultaneously. Okay? And when you do that, you need to start to keep track of the joint state of the 2 photons. Okay? And this is exactly what's going to happen when you study quantum computing, except it's going to be more than 2. It's going to be as many photons as you want. So we're going to try to answer a few questions today. The first question is, well, now if you have these 2 photons together, they're supposed to have a 4-dimensional state. So what is this joint 4-dimensional state? OK, that's question 1. And then once you get them together, you'll probably be doing some operations on them or some unitary transformations on them. Now, if it's some 4-dimensional unitary transformation, like we saw a couple of examples last time, then we know what to do. But in physical reality, right, you could just take one of the photons and do some little 2x2 unitary transformation to it, some 2-dimensional rotation, say. And then there's a bit of a type mismatch, it would seem. Like, how do you apply that to like a 4-dimensional vector? So we'll talk about that. So in particular, let's say if Bob applies, a unitary U, which is like a 2×2 matrix, to his qubit, what's the new 4D state? Okay, and we could ask an analogous question if Alice does some kind of transformation to her qubit. Let me continue our today over here. Okay, so that's talking about unitaries. And there's also sort of the part, generally at the end of an experiment or a quantum computer, where you measure your particles. And actually, this thing I'll put up, this question, I won't talk about it today. I'll talk about it next time. But it's the kind of analogous question. Let's say if we measure only Alice's qubit, what happens? It's a bit funny here because you actually know the rule for what happens if you measure the whole system. It's, you imagine you have a physical measuring device that takes in 2 photons and outputs the 4 possibilities. Well, now we call the 4 possibilities these, according to these squared amplitudes. But actually, you don't know the rule for what happens if you just take one of the photons and put it into a 1-photon measuring device. So we'll talk about that next time, actually. But what I want to emphasize in this lecture is that the answers to all the questions are basically what you guess is correct. And what I mean by this is, if I didn't tell you the answer and said, OK, think about it, like what would be the most logical answer to all these questions, then I think you would select the answer that actually is the correct answer. And you can, I also want to emphasize that you can guess all these based on analogy with probabilistic computation. So we've been talking, of course, about quantum computation and quantum particles. But there's a similar thing going on, right, if you talk about randomized computation. And these amplitudes are actual probabilities. You flip 2 coins somehow jointly, and they have these 4 probabilities of coming up the 2 different ways. Then you know probabilities, so you would know how to answer all of these questions. And the answers are exactly the same as we'll see in the quantum case. At least formally, like mathematically, you do the sort of same thing. And let me just add that as a corollary of seeing the answers to some of these questions today. At the end of the lecture, if everything goes well, you'll know all the rules you need to know in order to analyze quantum computing. So you'll have everything you need to know to understand quantum computing. And theoretically, you could start to learn about and analyze Shor's algorithm. I mean, it's a little bit similar to if I told you what a NAND gate was in Boolean logic and then said, OK, now you can design any computer algorithm you want. It's a little bit more complicated than that, but at least formally you'll know all the rules. OK. Any questions? All right, well, let's start then by considering this setup and trying to answer question 1. That's where I'll begin. OK, so imagine a little experiment where Alice has her own lab, and she sets up a photon in a certain qubit state, psi. And Bob has his own lab, and he sets up his own photon in a certain qubit state, phi. And then let's say they physically bring them together, because they're going to actually maybe do some operation that interacts with both of them. Or even if they're not doing that, you can nevertheless view the 2 particles, well, we say qubits, as a joint system, 4-dimensional system. OK, and it'll have some 4 amplitudes, which I'll call gamma. So gamma 0, 0 on 0, 0, 0, 0, 1, So you can view the two qubits as a joint system with 4 dimensions. And if you're going to start analyzing them, going through shared interactions, then you must view them in this way in order to get the correct analysis. OK, so the only thing we have to think about is like, OK, if let's give some specific values to Alice and Bob's states. OK, so say, Alice's psi is alpha 0, amplitude on 0, and alpha 1, amplitude on 1. And let's say Bob's phi is beta 0, amplitude on 0, and beta 1, amplitude on 1. OK, so the question is, when you view them as a joint state, what are these gammas? And as I was kind of suggesting here, if you think about it for 2 minutes and take a guess as what you think the answer will be, you'll be correct. And again, you can imagine it by analogy with probabilistic computing. Like suppose I said to you, Alice has like a biased coin that comes up heads with probability alpha 0 and comes up tails with probability alpha 1. And Bob has a biased coin that when flipped comes up heads with probability beta 0 and comes up tails with probability beta 1. And suppose they both flip their coins. What is the probability that you'll have 0, 0? What is the probability that you'll have 0, 1? That you'll have 1, 0, and that you'll have 1, 1. Okay? So let me just emphasize that in this, I wrote them vertically for no particular reason, but it lets me say this way that the first index here represents Alice's qubit, and the second one represents Bob's. OK? So by the probabilistic analogy, you would say, well, the probability that the coins turn out 0, 0 is the probability that Alice's coin turns out 0, which is alpha 0, times the probability that Bob's coin turns out 0, which is beta 0. And it's the exact same thing in quantum. OK, so it's just you can say this phrase. You can say these words to remind yourself of the rules. With amplitude alpha 0, Alice's qubit is 0. And with amplitude beta 0, Bob's qubit is 0. So, overall amplitude of 0, 0 is the product of these. OK, so I put this phrase in quotes because it's not this phrase is not exactly meaningful per se. It's not really correct to sort of say. These are not probabilities, so it's not exactly meaningful to say this. But this is just a phrase you can say to yourself to remind yourself of the correct mathematical rule. OK, so in fact, what I'm telling you is that it is the case in this picture that gamma 0, 0 is alpha 0, beta 0. Gamma 0, 1 is alpha 0, beta 1. Gamma 1, 0 is alpha 1, beta 0. And gamma 1, 1 is alpha 1, beta 1. OK, so that's the rule when you have 2 qubit states for what the amplitudes are when you consider them jointly. And just as a little check, right? This had better be a quantum state, these four gammas, which basically means the magnitude squareds had better add up to 1. And we can check that this is indeed the case, because what is the sum of the squares of the magnitudes of these 4 numbers? Well, the sum of the squares of the magnitudes of this, and this equals, I claim, alpha 0 magnitude squared plus beta 0 plus alpha 1 magnitude squared times beta 0 magnitude squared plus beta 1 magnitude squared. Why? Well, if you open up these brackets, you foil it, you'll get alpha 0 squared beta 0 squared, which is what you would get from here, and alpha 0 squared beta 1 squared, which is what you get from here, etc. Okay, and this is exactly 1 times 1 because psi is a state. So these two numbers squared add up to 1, and these amplitudes squared also add up to 1. Okay, so it is a genuine state, and that's the answer. So indeed, I'll just write the more general rule here. I showed you what is the rule when you take two qubits, in other words, two-dimensional states, and decide to call them a four-dimensional state. But more generally, if you have two qubits, you can adjoin them together and call them a joint state. And the rule is just what you'd get. So more generally, you can call this quantum mechanics law 4 if you wish. If Alice has a particle that's d-dimensional, a d-dimensional qubit, or sometimes called a d-level system, then that particle will have a state that's defined by d complex numbers, d amplitudes, whose magnitude squares add up to 1. And usually we call these basic states 1, 2, up to d. And if Bob, let's say, has an E-level state, okay, Bob has a qubit with E different basic states. So they don't even have to have the same dimension. Then Bob's state will look like beta 1 up to beta E. Okay, and these are also usually called 1 through E. Okay, then the joint state is d times E dimensional. Okay, so it's going to be a very tall vector of height d times E. Okay, and it's, like the probability, amplitude of having a 1 and a 1 is alpha 1 times beta 1. And the amplitude of having 1 here and 2 here is alpha 1 beta 2. E, alpha 2 beta 1, etc., all the way down to alpha d beta E. Okay? This is a d times E dimensional vector, and it's traditional to call the basis states, 1, 1, 1, 2, 1, E, 2, 1, etc., all the way down to d, E. Okay? And again, like sort of the first position indicates like the basic state for Alice's system, and the second position indicates the basic state for Bob's position. So if like Alice has a q-trit somehow and Bob has a q-bit, then their joint system has dimension 3 times 2, which is 6. Yep?
So I'm a little confused. So these probabilities would work out this way if, like, in a classical setting, if you threw 2 coins independently, and like in a classical setting, 2 coins being independent isn't so crazy of an assumption, right? Mm-hmm. But like, what would it even mean in this context? Do we, like, we're creating these joint states, but do we also have a joint measurement device? Because we clearly cannot have like 2 measurement devices back to back that would look at the first photon and the second photon, because then that would ruin everything.
Okay, good question. So there's sort of 2 parts to the question, or at least 2 parts of my answer. The first was about like, when I told this little story by analogy with probabilities, I said, oh, you flip the coins independently. And there's an analogous thing going on here in the quantum case. When I say, like, you take these 2 photons that maybe Alice and Bob prepared separately and then just view them as a joint system, you kind of are assuming mathematically that they haven't like previously interacted or anything, and that they're what we're going to call unentangled. Okay, that they're completely separate and they haven't interacted, and you just view them jointly. And then this is the rule for how you, name or work out the state of 2 unentangled, not previously interacting qubits or particles.
So you have to take for granted?
Yeah. So I mean, yeah, you have to assume that somehow at a high level these particles are like completely separated. They haven't, have any connections between them. And now, presumably you're viewing them in a joint state because you're about to do some interactions that involve both of them separately, or together. And therefore you would need to keep track of both them simultaneously.
Gamma 0, 0 could have just as easily been minus alpha 0, beta 0. That would have also preserved probabilities. Maybe when you combine these things, their amplitude would like reverses.
Yeah, like this is not like a proof that it had to be this way.
Yeah.
Just, you can accept this is like law number 4 of quantum mechanics. Like if you have two, particles that are like separate, they have not interacted before, and you just decide to start viewing them as a joint system, then like this is the mathematical rule for understanding what is the state of that joint system. It's to take all these like pairwise products.
Yeah, these joint measurement devices that work as expected with these things.
Good. So, right. So as for measurements, yeah, when previously, we talked about having like a d-dimensional qubit. It's kind of because we also imagined we had like a physical measuring device that had d different readouts. And so, when you put your particle with d-dimensional system into that thing, you could get d different readouts. They were named after the basic states. And so here, this kind of suggests that you have some physical measuring device that can take in two particles and give, one of d times e different readouts. And indeed, let's just say that that's what we assume. We have, like in this case, like some kind of like double photon reader that like spits out horizontal, 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 vertical, vertical, horizontal, or vertical, vertical. Now, as it turns out, and we'll see this, I'll get into this next time, you can actually build such a device by taking your two devices for measuring the photons separately and just, putting one photon into one device and one photon into the other device. But we'll talk about that separately because then, in order for that to make sense, you have to understand, like, well, what happens if you take like a joint state but only measure one of the particles? And that's something we'll talk about next time. Yep?
No, if we consider that we have a joint state, as you said, we assume that the particles do not interact with each other.
Yeah.
And if they don't, we can just measure them separately, and just from because the probability is proportional to alpha squared, what you said should be true. Explain why what you said about two separate measuring devices versus one together is not obvious.
Let me get into it next time. So what we're going to talk about this time is like what happens if you like take two photons that have their own states, and then you like pass them through like a magnetic field simultaneously that affects both their states. So it turns out that the right way physically and mathematically to model that is first you write down their joint state, which let's just say as an axiom is you do this. And then, if they're two qubits, you can apply your four-dimensional unitaries to them and so forth. And, we can pretend we're back in the last lecture and imagine we have like a four-dimensional measuring device. Now there is a funny thing, which is like we know, and this is what I want to talk about in this lecture, that like, well actually this four-dimensional state is coming from like two physical, photons or two physical electrons, and there's nothing stopping us from like, after getting them together jointly and then going through some shared experience, like you take one of them and you're like, hey, now it's a qubit and I'm gonna like measure it, or I'm gonna put it through this 2x2 unitary. Like, then what happens? So we're gonna talk about the second thing, the unitaries today, and we're going to talk about the measurement thing next time. It's not like the measurement thing is that much more complicated, but it's just it'll be better to do it in this order. Yep?
So this joint state still assumes that your two photons are distinguishable. It's not that you combine them, you can't tell which one's which.
Yes. Yep. Good. Yep?
Yeah, so another question is more about the previous stuff. So if you have 100 photons,
yep,
then you kind of said that the power is the joint state described by 2 to the 100, numbers.
Yep.
But there is like -1 dimension is usually 2 to the 100 -1. Whereas if you actually like look at this loss, it's described by only 100 numbers.
Yeah, that's right. Here, although this is a d times e dimensional vector, yeah, it came from only d plus e numbers.
Yeah.
So like these are the joint states are a very special subclass of all possible d times e dimensional states. They're the ones that we'll call unentangled later in the lecture. And by starting to do joint transformations on these two particles, you can get, yourself to like any d times e dimensional unit vector. And that's sort of the power. By like doing these joint operations, you can transform them into like a more dramatic set of possibilities.
So basically, what you're saying is that after you perform an operation on this joint state, the state is no longer kind of comes from two independent photons?
Right. We'll see all this in the next 10 or 15 minutes. Yeah. Yeah, and that's the beauty of it. Yeah. Good. So, yeah, we'll get in fact right into that. So, okay, so I just told you the rule, so I could just stop there and then go on to talking about unitaries. But now we have to take a linear algebra break to remind ourselves and or learn about like a concept in linear algebra. So there is a name in linear algebra for this operation, which takes in two vectors and spits out this vector. It's called either the tensor product or the Kronecker product. Hardcore linear algebra nerds will say those two things are not actually the same, Kronecker product and tensor product, but we're not going to be nerdy like that. We're going to ignore the distinction. If you don't know what I'm talking about, don't worry about it. If you're like a super math nerd, then don't complain. Okay, so if you have two vectors, they don't have to be the same heights, then this operation called the tensor product or the Kronecker product, and denoted thus, is the one that does this thing. It spits out a d e dimensional vector. Oops. Oh yeah. Sorry. Thanks. Alpha, beta, and alpha d beta e. Okay. So this is called the tensor product or Kronecker product. In quantum, they usually call it tensor product, so I'll probably start saying that. Good. Another way to write this same tall vector, it's kind of like a block vector, if you will. So I'll just write it slightly differently. You can write it as like alpha 1 times the vector b vector, alpha 2 times b vector, up to alpha d times b vector. Okay, this is a bit funny notation, right? This is a scalar times a vector, and then like we're stacking these vectors on top of each other. Okay. In fact, you can extend this Kronecker product to not just a vector product of vector, but just any matrix product any matrix. We're going to need that later, so I'll define it now, since we're here. So more generally, if you have some matrix A, like A1, 1, A1, 2, like A1, n, AM1, AMN. Okay, so if this is some m by n matrix, and let's say you have some other matrix B, which I won't give letters to, and let's say this one is P by Q. Okay, so they can be rectangular matrices of different dimensions. Then you can make a big matrix called A Kronecker product B, or A tensor B, and it's like a block matrix. It kind of looks like this. So it's like A11's the scalar times B times a copy of B, and then like A12 times a copy of B. Okay, out to A1n times a copy of B, and then like A21 times a copy of B, et cetera, et cetera, et cetera. And then the bottom corner, it's like AMN times a copy of B. Okay, so this is M times P by N times Q dimensional matrix. Okay, it's like a generalization of like, all pairwise products of the entries, like we saw over there. Okay? So again, it's this is the more important one for now, because it tells us how to take two qubit states and write down the state for the joint system. All right, so let me just do some examples. I'm not going to do the matrix examples. I'm just going to stick with these vector examples. OK, so let's say Alice has a qubit in state 0, and Bob has a qubit in state 0. Then what state is it when you put them together? Well, we'll just do it slow. 0 is, we also call it this vector, 1, 0. We Kronecker product with 1, 0. Okay, and when we put them together according to this rule, we get this vector, 1, 0, 0, 0. Okay, and that's very nice, right? Because when we have two qubits together, this was the thing that we liked to call, 0, 0. Okay, and some people just say that, well, this symbol is just formally like a short form or an abbreviation for this. Somehow this is like an example of the notation just working out super nicely. Okay? Any question about that? It's a little bit funny. And it'll work for the other four, right? If you do 0, tensor 1, you'll get the thing that has a 1 in this coordinate, which is what we like to call ket 0, 1. Okay, here's another example. Let's say Alice prepares a qubit in the state 0, and Bob prepares a qubit in the state plus. Remember this guy? This is 1 over root 2, 0, plus 1 over root 2, 1. OK. So then they bring their qubits together for a plate 8. And what is the 4-dimensional state of the result? OK, it's 1, 0, tensor product or Kronecker product, 1 over root 2, 1 over root 2. OK. And according to this rule, it's 1 over root 2, 1 over root 2, 0, 0. OK? Which we might also write as 1 over root 2, 0, 0. Right? This is the name of the first basis vector. This one, in other words, plus 1 over root 2, 0, 1. That's the name of this basis vector. And this should also look kind of pleasing, because it sort of looks like what we just did. It's kind of stuck these two together in the appropriate way, right? I mean, this was the state of Bob's qubit, which is the second column here. And we basically attached a 0 at the beginning. OK, so everything worked out nicely. Let's see. Suppose, on the other hand, that Alice prepares a qubit in state plus. And this gets to your question about whether the particles are still distinguishable after we put them together. We do consider them that way. And Bob prepares a particle in the state 0. Then what's the joint state? This is 1 over root 2, 1 over root 2, Kronecker product 1, 0. OK, and this is actually different. This is 1 over root 2, 0, 1 over root 2, 0. OK, which is also can be written 1 over root 2, 0, 0, plus 1 over root 2, 1, 0. OK, so again, on one hand, it looks like the right thing happened, right? You basically took this plus state and then stuck a 0 at the end. That's exactly what happened here. And of course, I also bring this up to demonstrate to you that this is not a commutative operation. OK, it matters the order you do it in. Yep?
Can you write ket plus 0?
Yeah, you can. Yeah, so you can also, people will call this, plus 0. Yeah, you can do it. That's the beauty of this notation. You can just do lots of nice things. Let's do one more example. So yeah, we'll do plus minus, if you will. Which is plus Kronecker product minus. Minus is the guy that looks like this but has a minus sign. OK, so that's 1 over root 2, 1 over root 2. Tensor product 1 over root 2 minus 1 over root 2. OK, which if you apply the rules is 1 over 2 minus 1 over 2, 1 over 2, 1 over 2. Perhaps. Yeah. Thank you. It's good. Maybe I did that on purpose to see if you were paying attention. Maybe I didn't. I don't know. Good. In fact, let me just scooch this over here because I want to just redo this calculation again. Right, let me do this using ket notation. So I could also write this as like, 1 over root 2, 0, plus 1 over root 2, 1, tensor product, 1 over root 2, 0, minus 1 over root 2, 1. Okay, it's all the same information. It's just these two numbers are sitting here. These two numbers are sitting here. And then, when I got these numbers, I did it by taking all the sort of pairwise products. And it's really just like what you would get if you kind of pretended this was like a multiplication and you distributed like in FOIL. All right, so you multiply these out and get the 4 possibilities. You get a half, 0, times 0, if you will, minus a half. Well, I'll start using the short form, 0, 1, plus a half, 1, 0, minus a half, 1, 1. Okay, but each of these stands for something that looks like this. Okay. So all of this is to say that this Kronecker product or tensor product, it's pretty much just, you can manipulate it formally like it's a non-commutative multiplication. So here are some very basic properties of this. Okay, that even hold for matrices, so I'll use capital letters. So as I said, it acts like non-commutative multiplication. By which I mean, if you do A plus B tensor C, it's A tensor C plus B tensor C. And the reverse, A tensor B plus C, A tensor B plus A tensor C. And it's associative, so like A tensor B tensor C is the same thing as A tensor B tensor C. These are easy to prove. Okay, and because of this, we drop all the parentheses and write A tensor B tensor C. So that's just like multiplication. It's non-commutative though, because as we saw, like it matters the order you do it. A tensor B is not necessarily equal to B tensor A. Okay, so as an example of this associativity thing, just to make it crystal clear. So, for example, if Alice has a qubit in state alpha 0, alpha 1, and Bob has a qubit in state beta 0, beta 1, and Charlie has a qubit in state gamma 0, gamma 1. Okay, and they decide to view them as a joint system because they're going to put all 3 photons together into some device, and they're actually also going to remember which one is which. Their joint state, okay, it's exactly what you'd think. It's like an 8-dimensional thing that's like alpha 0, beta 0, gamma 0, alpha 0, beta 0, gamma 1, down to alpha 1, beta 1, gamma 1. Okay, and the names of these coordinates, these 8 coordinates are 0, 0, 0, 0, 0, 1, etc. Okay. Let me continue just 2 more properties of this operator. Here's another one that's very easy to prove. If you have A tensor B and you dagger it, then you get A dagger tensor B dagger. Okay? You might have expected like maybe B and A should switch, but no, they don't switch. Okay? They always stay in their same place. Alice's piece of this and Bob's piece of this stay in place, but the dagger goes through like this. This is pretty easy to check if they're vectors. Okay, you can just imagine what would happen if you daggered this and daggered this. You would get the dagger of this coming out. Okay, and last property. This last property is actually, again, we don't need it yet. I'll mention it now. This one's like a little bit more annoying to prove, but I'm not going to prove it. We'll kind of see why it's true anyway. Let's say you have A tensor B. So that's a very big matrix. And then let's say you do a normal matrix multiply with C tensor D. Can we assume it's like the dimensions are properly set up so that you can do this matrix multiply? Then the answer is AC tensor BD. Okay, so again, the matrices that like to be in the first position stay in the first position, and those that are in the second position stay in the second position. Okay, so this is like some linear algebra computation woo-woo that you can just get used to. Okay, good. So actually, in some ways, that's where we'll end the story of what happens if you have, two or more states, and then you put them together and call them a new state. And now we're going to start to talk about, like, okay, now that you have these particles together, you presumably brought them together because you're going to do something jointly on them. So let's talk about how these big states transform. And we can even start to draw like little quantum circuit diagrams that become big quantum circuit diagrams when you actually really do quantum computing. Okay, so let's imagine that Alice, prepares a qubit. Maybe it's a photon. Draw like a little picture of, I don't even know what this is, some particle. And Bob has a qubit. And maybe they even prepared them in separate labs, but now they got them together. Okay, and before anything starts, once they get them together, these two particles have some joint state. And these are qubits, so the joint state looks like alpha 0, 0, amplitude on 0, 0, plus alpha 0, 1, amplitude on 0, 1, etc. Well, I omitted two things there. Okay, and now we're going to imagine we do something to them. Okay, so this is like a little quantum circuit diagram. These are like the two, let's say they're photons flying along, and then they enter into this box that like accepts two photons, and actually, they come out of it after having undergone some operation. And I'll draw a particular one. Okay, this box with this like plus and this bullet and this line between them is a mathematical diagram of a particular transformation called C0. Okay, which I think we mentioned last time, and if not, well, you looked at it on your homework in the context of probabilistic computing. Okay, so I'm going to tell you the mathematical formalization of what this C0 is. Now, in physical reality, you have to build a device that does this. And actually, this is where it gets quite hard. So from what I understand, physical devices that manipulate one qubit, they're pretty good at building them. They can pretty much build, a good version of whichever one you want. Whereas, like any physical device that operates on two particles together, it's very challenging to build. So like, I don't know if these are trapped ion qubits, and you have to like put them through some magnetic field. It's like very carefully chosen in order to affect this C0 transformation. In fact, according to Wikipedia, like the first time they really built a good version of these in practice, these like C0 gates, was in like 1995, which already post-dated like Shor's algorithm being published. But anyway, they've had 13 years since then, so I think they're pretty good at building physical C0 gates these days. But we're just going to assume, in this course that we have like a perfect C0 gate, and I will tell you / remind you what it does. Okay, so this is a picture of a gate or a physical device called C0, and it's a 4x4 unitary transformation defined as follows. Okay, it's 4x4 because it operates on 2 qubits. First, I'm going to define it in words, so this is slightly informal, and it's the words that you know from your homework. If the control bit, that's a technical term, which is the one marked in the diagram with the dot. So in this case, Alice's qubit, so control qubit, is 0, then do nothing. Else, meaning if the control qubit is 1, apply a NOT gate, if you will, to the target qubit. And the target qubit in the diagram is the one marked with this like O+ symbol, which in this case is Bob's. Okay, so that's like the words description. It's not completely formal, so let me say formally. The C0 operation, this 4x4 unitary operation, is the one that maps this basis state to 0, 0. I'll just write it and then we can look at it. This one to 0, 1. This one to 1, 1. This one to 1, 0. Okay, so you see it did what we said. This is assuming this first one is the control qubit, the second one is the target qubit. If the first bit is 0, then you just don't do anything. And if the first bit is 1, you swap the second one, or not the second one. Yes?
So it's assumed that this gate sort of doesn't measure the top qubit then?
That's right. It does not measure the top qubit. So this is not a measurement gate. This is a unitary transformation. So it just transforms one 4-dimensional state vector to another 4-dimensional state vector. Now, in fact, you might protest, like, how did I fully define it? Because as I said, it transforms one 4-dimensional state vector to another one, and it looks like I only told you what it does on 4 specific vectors, the standard basis vectors. But that's enough to specify it, right? Because it's a linear transformation, so it's enough to say where it goes on the 4 basis vectors, and it maps a general state, by linearity. So in fact, well, let me just write it all down. Okay, so I could further say, formally, that C0 is, this matrix 1, 1, 0, 0, 1, 1, 0. Okay, that's the matrix for C0, and it acts on a 2-qubit state, a 4-dimensional state, just by a matrix multiplication. And how did I get this? Well, the way to read a matrix, remember, is like, you mark the rows and columns. Oops. Okay, and then the first column represents where this guy goes. The second column represents where this basis vector goes, where this basis vector goes, where this one goes. Right, so this column is like it is because 1, 1 maps to just 1, 0. Okay, so say it yet another way, it maps this state to this matrix times this vector, which is sort of swaps the last 2 coordinates. Oops. Okay, and this is actually a permutation matrix. So as we saw last time, it's definitely a unitary matrix. I mean, it preserves the lengths of vectors. Okay, again, so let's say you have these 2 qubits. I'll finish writing this, are in this state. And you apply a C0, then at this next time, they have a new state when they come out. And again, you can say like it in the same words, or you can remind yourself with the phrase that you would use if this was all probabilities. You would say, oh, with probability alpha 0, oops, I should say amplitude alpha 0, 0. Fake correcting myself, it's in the state 0, 0, in which case it maps to 0, 0. And with amplitude 0, 1, it's in the state 0, 1, so then it maps to 0, 1. And with amplitude alpha 1, 0, it's in the state 1, 0, in which case it maps to 1, 1. And finally, amplitude alpha 1, 1, it's in the state 1, 1, and it maps to 1, 0. Okay, that's just a phrase you can say to yourself to remember the formal linear algebra rule. Okay, any questions? Okay, so let's draw now our first interesting quantum circuit. Little quantum, I don't know, algorithm or device that you might cook up. So let's keep this. And this is something that like quantum computer people and quantum mechanics people love to do, this specific little circuit. So generally, in all experiments or quantum computers, you actually typically assume that like the qubits are initialized to 0. That like Alice, the first qubit's initialized to 0, the second qubit's initialized to 0. That's the standard thing. And then let's do this. Let's imagine that Alice first passes her qubit through a Hadamard gate. I'll remind you of that one. And then they pass both their particles through this C0 gate. Okay. And in fact, Alice could have done like this part, before she met up with Bob. She could have done it in her own lab and like brought her particle over to Bob here. I mean, they definitely have to get together, and you have to start treating them as a joint state when they're about to enter this gate together. But just for simplicity, let's start, treating them as a joint state even back here. It's fine. So in fact, let me say this is the little thing we want to analyze. You can think of this as like time. So I'll just call this time 1, this time 2, and this time 3. Okay, I just want to work out what is the joint state of the two particles at each of these 3 times. Okay, so what is the state at time 1? Well, this is an easy one. They're like, 2 particles in state 0 and 0. We just brought them together for the first time, so it's just 0, 0. Okay, 100% amplitude on 0, 0. And then Alice applies a Hadamard to her gate, so, her qubit. So actually, I guess we didn't quite talk about this, but we can still understand what it'll be, right? So at time 2, you can actually pretend like Bob is not even in the picture yet. So Alice has applied a Hadamard to qubit in state 0. So Hadamard, if you apply it to 0, it gives you plus. Okay, that's part of the definition of Hadamard gates. The other part is that if you apply it to 1, it gives you minus. So you can think then, okay, at this point, Alice has actually prepared plus, and then Bob comes along with his 0. They still haven't interacted. So the state at time 2 is, plus tensor 0. Okay, and we worked this out earlier. This is the state 1 over root 2, 0, 0, plus 1 over root 2, 1, 0. Okay, it's just like you took the plus state, 1 over root 2, 0, plus 1 over root 2, 1, and you like attached a 0 on the end. Okay, so far so good. Now the slightly interesting thing is going to happen. Okay, so now we have the particles, and like this is their joint state at time 2. So let's figure out their joint state at time 3. And we kind of talked about this already, right? I mean, it transforms exactly like this. So your amplitude on 0, 0 and 0, 1 stay the same, and you swap the amplitudes on 0, 1 and 1, 0. So this part stays the same, and this switches to 1, 1. So it's 1 over root 2, 0, plus 1 over root 2, 1, 1. Okay, and that's the end. Any questions about the calculation? Okay, good. So this is a very important state. Like, people love this state. It's like such a cool state. It's a great state. It's called the Bell state. For reasons we'll see, I don't know, in a couple of lectures. And it's such a great thing that, like, let's give it 2 names. So, like, the state is called the Bell state. And if you have 2 particles in this state, the particles are called EPR pair. I'll use these terms indistinguishably. I actually prefer to call them EPR pair. EPR stands for 3 physicists, Einstein, Podolsky, and Rosen. And they got together because, it was, I guess, the 40s? I'm not sure when they got together to talk about this. But they didn't believe that the laws of quantum mechanics were complete. They were like unsatisfied with like all these like weird things involving interaction and entanglement and measurement that we're going to talk about later. And they kind of cooked up this state and used it to illustrate a paradox in quantum computing. And so it's the EPR paradox. And then later, people were like, nope, there's no paradox. That's perfectly fine. So I'll talk about this whole thing later, but like this is just to say why this state got the name the EPR pair. But as I said, it's a very interesting state, and you can do lots of interesting things, like once you get your photons out of this tiny quantum circuit. Good. So let me just also, you can write it like this: 1 over root 2, 0, 0, 1 over root 2. That's how you would write it as a 4D vector. So now I can actually come to answer a question that Alex asked quite a while ago about like the set of all possible 4-dimensional vectors that you can get in a 2-qubit state. Let me prove a little theorem. Perhaps it's the first theorem we've proved in this course. Can't remember. But the Bell state, this is what I'm going to prove. The Bell state is not of the form psi tensor phi for any 2-qubit states, phi and psi. Okay, so how do you think about this? Like, it says that this state cannot arise by taking like 2 totally separate particles in their own qubit states, bringing them together and saying, hey, I'm just calling this a joint state. In other words, the only way this state can arise is if these particles somehow interacted together at some point. So let me give you the proof of this. Okay, whenever you have, let's say, psi is alpha 0, alpha 1, and phi is beta 0, beta 1. We know the product here is alpha 0, beta 0, alpha 0, beta 1, alpha 1, beta 0, alpha 1, beta 1. Let me just, whenever you have this situation, let me make a tiny little cute observation. The product of these 2 amplitudes equals the product of these 2 amplitudes. Okay, so second times third amplitude equals the first times the fourth amplitude. Right? Because they're both equal to alpha 0, alpha 1, beta 0, beta 1. Okay, that's just a teeny tiny observation. But that's not true of the Bell state. Right? The product of these 2 is 0. The product of the first and fourth is a half. So that's the end of the proof. Okay. So in fact, we make a definition for this kind of state. This kind of multi-qubit state, in particular, for this kind of 2-qubit state. So let me just circle up part of this. Okay, any state that satisfied this circled part is called entangled. Okay, and this is just an adjective that like sometimes gets used casually. But like, if you want a formal definition, it's this. It means it's not of the form, one state tensor another state. Okay, and the opposite of this is unentangled. So in fact, once you have these adjectives, it's kind of self-referential. You say like, oh, if you have 2 unentangled particles and you decide to view them as a joint state, then this is the rule for what the joint state is. And I should mention, it's not very obvious by looking at a state whether it's entangled or unentangled, generally. It's also often not important to recognize this. Well, sometimes it's useful to be able to recognize the unentangled case. But let me just say as an example that's like not so obvious. Here's a state. 1 over root 2 times, I'll take advantage of some linear algebra notation to factor out the 1 over root 2. Well, let me not do that yet. 1 over root 2, 0, 1, plus 1 over root 2, 1, 0, plus 1 over root 2, 1, 1. And ask, is this state entangled? Sorry, these should all be halves. That's probably what you're grumbling about? Yeah. Good point. Okay, we need their squares to add up to 1. Is this state entangled? At first you're like, man, it looks like even more like complicated than this state, right? So maybe yes, but actually no. Okay, it's not because it's, well, it's plus tensored with plus. Okay. Yeah.
Is the reverse true if the second and third is equal to the first and fourth?
I think so. Maybe that's a little puzzle for you if you have two qubit states. I think if the product of these two equals the product of these two and it's a unit vector, then I think it's entangled. But this, if that's true, check it. Then something like that's probably only true in the case of 2 qubits, 4-dimensional vectors. It's like harder to recognize if you have, I don't know, product of 2 qubits, for example. Yeah.
So it's possible to have 2 separate entangled things, pass them through the same gate, and still have them unentangled.
Yes, it's possible that you have, you say unentangled things, pass them through a gate, and they're still unentangled? Yeah, it's possible. What's not possible is to, have unentangled particles and entangle them without passing them jointly through a 2-qubit gate. Okay, if they're always, you only pass them through like 1-qubit gates, you can have a bunch of them, they'll remain unentangled. They can only get entangled if you do like a joint operation on them. Yeah?
Would it be correct to say that a state is entangled if you know one component affects the probability of knowing the other components?
I would say no, because I don't even exactly know what you mean by probability there. These are amplitudes, they're not probabilities. Now you could imagine measuring them, and then maybe try to start to talk about it, but I would really prefer to just say, like very plainly mathematically, entangled means not of a tensored form.
Right.
Yep.
Would it be possible to unentangle an entangled state of the gate?
Ah, that's a good question. What do you think?
Intuition says no. I'm not really sure.
Yes, maybe? You can do the inverse
Yeah.
of a unitary.
Right, so every unitary, we saw last time, is invertible. So every unitary transformation has an inverse transformation. In fact, for a lot of the ones we like to happen to use, like the C0 gate and also the Hadamard gate, it's its own inverse. It's kind of a coincidence that like our favorite ones tend to have this property. It doesn't have to be this way. But the C0 gate is actually its own inverse. If you do it twice, you get nothing. So yeah, so at this point, they're entangled. But then, if we put them through another C0, they would go back to the same state they were in here, which was unentangled. So yeah, it is possible to unentangle qubits.
Question. So you said that even the 2 qubits are in the entangled state, we can still take only one of them and apply some transformation.
Exactly what I'm about to talk about, yes. That's right.
How does that work? Like even physically, no? Like
Yeah, it's funny. It's funny. So at this point, once they become entangled, now definitely nature is keeping track of a 4-dimensional vector. Because in order to understand what will happen to them in the future, you can only do that if you keep track of their joint state. But it's also true that these are literal physical particles, and there's 2 of them. And like Alice can okay, I'm saying it in a funny, casual way, but like Alice can pick hers up, or like pick the super cool refrigerator that it's stored in up, and just like walk away with it, and like walk like super far away, and they remain entangled. I mean, if you're very careful not to like disturb them, which is hard in practice, but theoretically possible, and they can do it. yeah, she can like walk away, and then, for example, she can now say, oh, I'm going to apply a NOT gate to my qubit. And something's got to happen, right? And that's exactly what I want to talk about. Oh, shoot, in my notes I did it the other way. I had Bob walk away. Let's do that. That's sneaky Bob. Yeah, so what happens? I mean, this can happen.
Why don't we use this for communication?
Oh, we'll get into that. Don't you worry. It's a very good question. It's a very good question. Because Bob's local action here changes the joint state of the two particles, which is kind of amazing. Like, so to understand like what will happen if Alice does something, you need to remember that her particle is entangled with Bob's. And Bob's, could have taken his particle very far away. We're going to explore all this later. Yeah. I mean, this is what Einstein, Podolsky, and Rosen really hated. But they did it. They can do it. We'll see that a few years ago in the Netherlands, they literally did this with one experiment. These two particles were 2 kilometers away on the university campus, and they still did these experiments that demonstrated all these crazy things about entangled states, which we will talk about in upcoming lectures. Today, sadly, we just have to learn the rules of how to manipulate these so that we can become amazed later. Okay. So what happens here? You see there's some kind of type check problem, right? I mean, at this point, their joint state is a 4-dimensional vector, but the NOT gate is a 2x2 unitary, and you cannot apply a 2x2 unitary to a 4-dimensional vector. So what happens? Well, there's rules, and I will tell them to you. But again, the rule is basically the thing that you would expect. Okay? So in fact, let's say we do exactly this. At time 3, this is the state. Let me erase this. Okay, and then let's say Bob takes his qubit, says thank you, and applies a NOT gate to it. What would you guess is the new state? The new joint state? Yeah?
Well, the new joint state is just what you would expect the state would be if Bob's bit were knotted. So 1, 0 would become 1, 1, and because Bob is the second bit. And 0
becomes 0, 1.
0, 1. Yeah.
Okay, so what would it literally be? Just tell me the numbers.
1 over root 2, 0, 1, and 1 over root 2, 1, 0.
Yeah, that's right. Okay, so that is the correct state after you apply the NOT gate to the second qubit, the 2 qubits in this state.
And they're still entangled.
They are still entangled. The physicists have a name for this one. They call it the singlet state.
How does this apply not to Bob then? You're literally applying not to everything.
I will tell you the rules now. I mean, this is an example. So in fact, let me tell you. I mean, basically, it's exactly what you would do, and you had this in your homework, as if this was probabilistic computation, and these were representing probabilities, not numbers, right? You would say to yourself, if this was probabilities, somehow Alice and Bob were flipping coins and got into a situation where with probability 1 over root 2, this doesn't make sense because they don't add up to 1, but with probability 1 over root 2, it was heads, heads, and with probability 1 over root 2 is tails, tails. And then if Bob, flipped his coin, then you would say, all right, now the new state is probability 1 over root 2 that it's 0, 1, and it's probability 1 over root 2 that it's 1, 0. Okay? So you just use the same intuition or rules that you would use as if it were probabilities, like you did on the first homework, and that's the answer. So let's do a more tricky example to illustrate. Okay? I should mention that when I was first learning quantum computing, this is the part that confused me the most by far. I just could not understand how do you apply a 2x2 matrix to a 4-dimensional vector. But just imagine the probabilities and these are coins and it's the same rules. So let's imagine that okay, Alice takes, let's imagine it happens temporally afterwards, although it actually doesn't matter. Alice applies the Hadamard gate to her qubit. Okay, so we're going to get into this state at time 4. This is a horrible diagram. And then at time 5, this will be the last one, so I'll just end it like that. What is the new state? Okay, and just say the words as if they were probabilities, right? So you say, okay, with amplitude 1 over root 2, the state is, I'll put these in quotes because like probably quantum physicists and mathematicians will get mad at you for writing these words on paper, but just say these words to yourself. The state is 0, 1. Okay, and remember, like, this is Alice's qubit, this is Bob's qubit. Okay, and let's expand this out to, like, this is, 0, tensor 1. And now, applying h to Alice's bit, qubit, yields, well, you just do it. Like h applied to 0, tensored with 1. Okay, and we know this is plus tensored with 1. Just write it out. This is 1 over root 2, 0, plus 1 over root 2, 1, tensored with 1. And then we like distribute. So it's like 1 over root 2, 0, tensor 1, plus 1 over root 2. Tell me if I'm making a mistake, by the way. 1 tensor 1, which we write in shorthand as 1 over root 2, 0, 1, plus 1 over root 2, 1, 1. Okay? And we're halfway done the computation. So like we took care of this part. But there's 1 over root amplitude that it was 1, 0. It's 1, 0. And again, this is Alice's part. This is Bob's part. Okay, and all right, this is 1 tensor 0. Then applying h to Alice's qubit gives h1 tensor 0, which is minus tensor 0, which is 1 over root 2, 0, minus 1 over root 2, 1, tensor 0. Okay, and we expand that out and get 1 over root 2, skip one step that I did before, minus 1 over root 2, 1, 0. Okay, and now we're mostly done, but like now we say, okay, we've got to multiply this amplitude times this, and like this amplitude times this, and like add them all up. So finally, the state at time 5 is, let's see, how much 0, 0 do I get? I get 1 over root 2 times 1 over root 2, 0, 0, 0. How much 0, 1 do I get? I get 1 over root 2 times 1 over root 2, which is another half. Actually, in this calculation, you'll see that like nothing ever cancels or like affects one another. I happen to get like 4 different things and they're separately, but in general, like, you could have some, 1 1s here and also some 1 1s here, and then you have to add up the coefficients. This is what's known as interference. Okay, where was I? You get a half times 0, 1. Okay, how much 1, 0 did I get? I got the product of these two, so negative a half, actually. And I think it's this, a half, 1, 1. Okay, so that's the final answer for what happens when you take this state and you do a Hadamard gate to the first qubit. So study this example in the future. Like if you're ever confused about what happens, more generally you might have like 5 qubits and you do a 1 qubit gate to the third one, or maybe you do a C0 to like the second and the fifth one. It's starting to look complicated, but like you just apply the rules you would apply if they were probabilities. Okay. was actually going to do an example of doing a C0 to the first and third qubit in a 3-qubit system. I won't have time, so you can look at the notes for that. OK, so actually, I could just say, like, we're done. You now know the rules of how to apply a unitary transform to a subset of the particles in a multi-qubit system. But let me, in the last 5 minutes, tell you, like, the slick linear algebra symbols that you can use. Okay? Just in the same way, after I told you how to, like, get the joint state of 2 qubit states put together, it was like the Kronecker product. There's some similar, linear algebra symbolism that you can use to talk about applying unitaries to multi-qubit states. Okay? So I'll just do it again, sort of by a bit of an example. So say in general, we have a 2-qubit state. And it looks like this: alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. It's 4-dimensional. And suppose we have a 1-qubit unitary. So that's a 2x2 unitary. And let's say its matrix form is P, Q, R, S. And, suppose we do U to the second qubit. I could have written second or first here. Let me just say second, for example. Yeah, then you can ask, what is the new state? Okay, and again, it looks like a type check issue, but we know the rules. So let's do the rule in this general looking scenario and see what we get. So I need to understand, what the new state will be after I apply this to the second qubit of this. Now this is like very annoying. There's like 4 different amplitudes here, but I can assume sort of without loss of generality, or I can only worry about, it's not quite a right use of the phrase, but we only really need to worry about, the initial state being 0, 0, one of the standard basis states. Because once we figure out what happens to these 4 states, then we know what happens to any 4-dimensional state by linearity. I should mention, by the way, that like the final action of doing this to the second qubit will be the action of a 4x4 unitary. We know that like any transformation to a 4-dimensional state is given by a 4x4 unitary. We're just trying to figure out like which 4x4 unitary is it. Somehow comes from this matrix. Okay. So let's see what happens if you are in this state and you do the unitary U to the second qubit. Well, okay, let's just do it kind of slow. So this is the same as 0 tensor 0. And we're applying U to the second qubit. So U on the second qubit. We get 0 tensored with U0. Okay, and U0, where does U map the 0? It maps it to the first column of U, which is PQ. Okay? So let's switch to coordinates. This is 1, 0, and this is PQ. Okay? And what is that? Well, it's PQ 0, 0. So we actually figured out that doing this takes the state 0, 0 to this 4-qubit state. Okay, now we just have to work out 3 more things like this, which I'll do rather quickly. So if you're in state 0, 1, which is 0 tensor 1, this maps to 0 tensor U1, okay, which is 1, 0 tensor the second column of U, which is RS, which is RS 0, 0. Okay, let me leave the other 2 as exercises for you. Okay, well, I'll just tell you. This one goes to 0 0, PQ. And this one goes to 0, 0, RS. Okay, so the overall transformation, we know where the 4 basis vectors go, so we can write down the matrix for the overall transformation. The overall transformation is a 4 by 4 unitary. And this is 0, 0, 0, 1, 1, 0, 1, 1. Whereas it takes 0, 0, it takes it to P, Q, 0, 0. This one goes to R, S, 0, 0, 0, 0, P, Q, 0, 0, R, S. And if you remember all the way back to the Kronecker product, this is actually the 2 by 2 identity matrix tensored with U. And what I want to tell you is this sort of makes sense because, you know, we said we did U to the second qubit. You could say, what did you do the first qubit? Well, we did nothing. Well, what is the unitary transformation for doing nothing? It's the identity transformation. So it's better to say, oh, I did U on the second qubit and I did nothing on the first qubit. So now I have two 2 by 2 unitaries that I sort of jointly did. And therefore now you kind of will not be surprised to learn that the overall 4 by 4 transformation is this Kronecker product. Okay, and conversely, I can leave it to you to check that if you did U to the first qubit and nothing, in other words, I to the second, the overall transformation is U Kronecker product I. And if you actually at the same time did V to the second qubit, where V is a 2 by 2 unitary, and you did U to the first qubit, then it's U Kronecker product V. Okay, so I'll maybe recap this a little bit next time, but you now know the rule, you now know the linear algebra formalization, and actually you now technically know everything you need to know in order to build and analyze quantum computers. But we'll get into many more details in future lectures.